Thank you, Professor Hoshimoto, for the wonderful talk. And as you can see, the audience has responded quite enthusiastically. A lot of questions have come in. So without any delay, let us start with the Q&A session. The
Okay.
first question, Professor Hoshimoto, is from an early career researcher who wants to know about why these complexes are termed as frustrated.
Can I? Sorry.
So why these complexes, the ones you showed, are termed as frustrated? So why are FLPs called frustrated?
It's interesting question. So maybe you have to ask Doug Stephen, who named FLP. But okay. So generally, Lewis base and Lewis acid would like to make a bond. Okay, this is general trend, but they have more large steric bulkiness, so large steric repulsion. That's why they cannot make a bond, but they want to make a bond. This is a frustration between molecules. They would like to make a bond, but they cannot make a bond. Then make a Lewis basic lone pair and the Lewis acid empty orbital is pre-organized like this, not make a bond, that's the pre-organized with a frustration. Then it's concertedly or cooperatively work for the to show the very high reactivity. Okay, this is the answer.
Yeah, thank you, Professor Hoshimoto. That was very clear. So moving on to the next question. This is about, so where the participant is asking, have you thought of any other methods to trigger the conversion of classic Lewis acid pairs to FLPs, for example, light or chemical triggers?
That's a good question. Yes. So far, we not. But after developing the thermal responsive systems, we considered about light responsive systems, but we have no such good idea to achieve that. But later, Doug Stefan achieved the light responsive structural conformation change for the generation of FLPs. So we not, but the other group did.
Okay.
It's okay. Yeah.
Thank you, Professor Hoshimoto. So moving on to a very specific question.
Yeah.
Participant has asked, do you observe over addition to give alcohol during the synthesis of asymmetric ketone?
No. Oh, it's okay. It's okay. Okay. It's depending on the nucleophile you use. If you use the more reactive, so lithium, organ lithium reagent or Grignard reagent, of course it happens. Yeah. So why we use the zinc is reactivity is very mild and easy to regulate. And one point is coordination of such molecules to zinc is very, this is important point to regulate the reactivity of zinc components. Okay, this is the answer. Okay.
Yeah. And just as a follow-up to this question, Professor Hoshimoto, how does this method that you show here using POXIM compare with other methods of CO2 conversion to ketones that are available in the literature?
What do you mean? I can't get that meaning. Okay.
So you have shown this CO2 transformation to unsymmetrical ketones. How
Yes.
does this method compare with other methods that are available in the literature?
I see. Okay. So simply thinking, you can try to use lithium or magnesium reagent to convert the CO2 to not unsymmetrical is okay, but it's ketone. But once you form the ketone is more reactive than the CO2 itself. So if the nucleophile is there, nucleophiles attack to ketone, then you can get the tertiary alcohol or further substitution give that's simple alkane. That's why using the organometallic reagent for CO2 conversion to ketone is very difficult because the ketone is more reactive than CO2. That's the problem. Okay.
Okay. Yeah. Another question on the isolation and storage. So what makes isolation and storage of FLPs very difficult. So this is also a basic question that the participant is trying to ask.
Because it will soon decompose because of the molecular frustration. So means, for instance, so yeah, I explain for examples. In this case, they would like to make bond between hostpin and boron, but they can't because of the huge steric repulsion. Thus, this P attack to the paracarbon in BCF soon, and it's decomposed. Or in these loose cases, you can only observe this species or this species when you try to isolate. That's why it's difficult to isolate the FLP. Okay, is it okay?
Yeah, thank you, Professor Hoshimoto. So just as a follow-up to that, what is the rate limiting step in the formation of NHC FLP pair?
You're probably talking about this reaction, is it? Maybe this reaction, right?
Yes, yes.
I think so. Yeah. Late determining step or more, the step has most activation barrier is this jumping process. But this is the energetical bottom. So this is most stable in this system. But in the presence of hydrogen, dihydrogen, this is a trick, okay? In the presence of dihydrogen, hydrogen activated product is the most stable, okay? That's why this reaction proceeds thermodynamically, okay? So the late determining step is, so this all processes increasing energy. So this is the motto, and the most highest energy is the activation, H2 activation pathway, H activation process. However, so when we see the elementary step level, this process has a huge energetic barrier, which cannot be overcome at room temperature. Okay.
Yeah. Thank you, Professor. So the next question is from a participant who is asking, how difficult is it to access mixed substituted boron-Lewis acid with different chloride systems?
Yeah. Once you achieved synthesis, you can easily access to such molecules. So difficulty is fast try or to establish the synthetic process. Yeah, this is always in organic synthesis, right? But there are several methods to introduce different allyl groups on the brain. So it can, but the first try or first success is always very, very difficult. And our student took 2 months or 3 months to achieve the one structure. But after they achieve the establish the synthetic procedure, they can make within 3 days or 2 days in a gram scale. Okay, so there is a critical differences reported by Meren or Totmada, so you can check that differences.
Okay, yeah. Thank you, Professor. Where the participant is talking about your last part on
Last part, okay.
So are there any other molecules like BCF for purification of molecules other than hydrogen?
I see. Of course. What you want to do is the problem. Okay, so this is better. No, I'm sorry. Okay, this is better. So in this case, we collected hydrogen by via dehydrogenation reaction. If we don't do dehydrogenation, you can just remove hydrogen from crude gas. Okay, so if you input, for instance, if you input H2 CO2 gas here, then hydrogenation just remove H2, then you can get the highly purified CO2. Can you get meaning? Okay, so you can remove, so you can separate the gases by using these techniques, and just removing H2 removing here, and you can recorrect H2 here. So this is the H2 purification, right? Okay, this is the answer. Okay.
Thank you, Professor. So about the front and back strain strategy that you have shown, so what is the role of fluoro or other halogen substituents in the boron?
Good. Okay. So in our optimized catalyst here, okay. So this load of this chlorine to get the front strain. Okay. This makes the front strain. And these guys, this meta position, metabromine, metachlorine, making a back strain. And the protonation here is regulating the electrophilicity of borane. Okay? If you'd like to change borane's reactivity drastically, first choice is electronic regulation. Of course, this is very strongly change the reactivity of boranes. Okay? The first strategy is electrophilicity regulation by changing atoms on aryl grids. Okay? Then front strain moderately regulate the reaction and reactivity, moderately regulate the reactivity, and backstrain, finally, backstrain, finally regulate the reactivity. Okay, that's the, I think, general procedure in our group. Okay. Is it okay?
Yes, Professor. Thank you. So I have a very specific question from a participant who is asking about slide number 45.
Slide 45. Okay, now we are 44, 45. Okay, good.
Yeah, so the participant has mentioned the formation of starting material, that is quinoline, is showing 174% was detected as a side product. So was it evaluated as a pure isolated side product, or was it optimized as crude from NMR or some any other technique?
Okay, so this reaction is very clean, very clean. And we are monitoring this reaction by using GC analysis. Okay, GC analysis. I believe generally reaction proceeds quantitatively. Okay, but there is some measurement sensitivity or other. So yeah, this 91% or 194% because after this reaction, we once do the sampling, so reduce the amount of substrate, discard a little bit. Okay, then we cannot achieve 100% in the next stage. Of course, because we throw away some samples for the detecting GC. That's why it's a little bit decreased. But basically, if we can conduct it in a completely closed system, maybe it proceeds quantitatively well. Okay, and we corrected. So this is 174% means we corrected the gases from the silicon oil, like this silicon oil corrector. Okay, and we check the this yield from the corrected volume of H2. So it's a little bit rough. That's why I think so. But the system is very clean, I think.
Yeah. So thank you, Professor. I'll take up another question where the participant has mentioned that the generation of hydrogen may come from biomass, as you mentioned in your presentation. So participant would like to know more on that. Like if you could share some more insights on how that method could be feasible.
Okay. Now it's developing technology in many countries, especially, of course, in America, of course, in India and Africa, South Africa, or many Asian countries. But these biomass so for instance, wood waste or some other biomass waste can be gasified to turn into the gas by burning or some other gasification technology like coke or some other carbon-based material. Then you can get the crude hydrogen, or some other biomass can be transferred into methane CH4 by fermentation. Okay, bioprocess fermentation. Then methane can be transformed into hydrogen and CO2 or some other method. So that strategy is now developing, and I believe it's really nice for the sustainability. It's called waste to hydrogen, so waste to electricity or waste to power strategy. Okay, so you can check such word in the Google. So maybe Google teacher can teach you more better than me, right? Waste to hydrogen strategy. Okay.
Thank you, Professor. So there's a question on so there's a question where the participant is wanted to know on the challenges of interaction of NHC with amino acid.
Oh, that's good. That's good question. Yeah, I completely omitted it today. This one, right? This one, right? Yeah. At this moment, we are developing application of this PMM species. And now we are finding very interesting aspect of this PMM systems. Will be soon. I hope we'll soon report. But at this moment, this anti-structure is key, because if PMM has a syn structure, these CH bond or these reactive site can be easily quenched by this carbene. But this anti-conformer protect these reactive formation or reactive parts from the carbene itself. Once you use the carbene for metallation or something other transformation, then rotation should cause any problems. Okay. So because this is stable molecule and the anti-conformation is very important in this case. Okay.
Thank you, Professor. So the next question, I guess,
many questions. Okay. I'm happy. Yeah.
Last couple of questions. Thank you, Professor, for taking your time to answer the questions again. So what is the reason behind syn conformation of HOTF ligand?
Okay, I see. Yeah. So yeah, please pay attention. This is the solid state structure. Okay, this is the key point, solid state structure. And why this guy has the syn conformation is in the crystalline lattice, they can make a hydrogen bond each other. Okay, this proton and this oxygen intra and intermolecular can make a hydrogen bonding. That's why in this case, making a syn orientation. But in solution, I believe he can rotate easily. Okay. Okay.
So thank you, Professor. I guess we are almost on time, and I would request you to provide any closing remarks that you may have on the scope of research in this field.
From me?
Yeah.
Closing remarks from me?
Yeah.
Yeah.
On the scope of research in this field.
Okay, so today, so thanks so much. Thank you very much for attending my lecture today. I am really happy to share our chemistry, and I can check your question. I will answer possibly as many as possible. I will answer your question by using chat, or I don't know how to, but I can maybe either answer. Okay, so our works is of course going on. And the two projects. So first project, Poxin project is, as you can see, a little bit fundamental chemistry. But later, trial project, so crude gas project is engineering, so oriented to the engineering. We have very fun in these two projects, and very happy to report next result in near future to you. So thank you very much for attending today's my lecture.
Thank you so much, Professor Hoshimoto, again, for your time. Kunal.
So, thank you so much, Professor Hoshimoto, for that wonderful lecture and for your patient answers to so many, as you mentioned, so many questions. And this is the feature of our program, Science Talks, which basically is about having an interactive session. So I'm sure the audience members have enjoyed, and you can see so many reactions popping out with so many different types of emojis being sent. So thank you so much. So with that, I think I'm going to close the session. So this brings us to the end of today's session. We hope that you have enjoyed this broadcast. We invite you to view the edited recordings from the past events in the ACS Science Talks library. At the end of the session, you will receive a brief survey. Kindly share your feedback with us so that we can continue to improve and serve you better. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS events. Until then, stay safe and healthy.